Hi, I'm Lee Teschler with Machine Design Magazine. We're here with Aaron Ames, Professor Aaron Ames from Texas A&M. And Professor Ames heads up an experimental robotics lab at Texas A&M, and he has a bipedal robot platform working here behind us. Professor Ames, tell us a little bit about this demonstration you put together. It's pretty interesting.
Well, thank you very much. What we're trying to do is really capture the fundamental mechanisms of walking. So we want to create robots that have the same capabilities that humans have. And this is a very complex task. There's lots of, complicated control that humans do, but what we're arguing is that at the fundamental level, control for robotic walking is fairly simple if you understand what's happening. And we're trying to capture that with this robotic platform and get robots that can really achieve what we do every day with ease, with ideally equal ease. Yes.
Can you tell us a little bit about the sensors that are in the robot legs right now?
The sensing is actually fairly basic. We look at encoders, so we read the angles of the robot, and we have foot contact sensors, which tells us which foot is on the ground. And that's all the sensing we actually need to achieve locomotion. So really, the art here is not the sensing. The art is the control that underlies it all, and finding that fundamental universal control that humans seem to display. So we actually start at the level of looking at human walking, and we study human walking and try to really, take out that essential, extract that essential information, and then we encode it in a formal way in simulation, and finally on the robotic platform itself. Yeah.
I understand that a lot of the time the robot is kind of off balance. Can you tell us how that works into the algorithm?
Yes. Well, walking itself is what's called dynamically stable, which means that if you stop the walking at any point in time, it will fall over. So you need to create dynamically periodic motions that are stable, but not in a traditional sense. So the idea is to create and capture that behavior to get this much more human-like walking gaits that distill out. So to do this requires a lot of math, a lot of algorithms, a lot of programming, but in the end, if you can get this sweet spot in walking that we display with ease, you'll find that robots are incredibly robust and able to do exactly what we do despite the differences between the physical hardware and our human bodies.
How big of a program have you got to do the demonstration that we're viewing here today? Is that pretty complicated?
Yeah, it's very complicated. We use something like 7 programming languages, different platforms from Mathematica, MATLAB, LabVIEW, all the way down. And not only that, but the program itself is thousands and thousands of lines, and it's very complex and very time-consuming on the computer side. But the amazing thing is once you understand what's happening at a fundamental level, you can use all that to extract out a single, very small amount of data that completely represents walking. And it's that small amount of data that we implement on the robot that you saw today. So in the end, walking is simple, and what we're seeking is this simplicity on the far side of complexity.
This robot, to find out if it's stable or not, are you using anything like a gyroscope?
No, actually. In fact, the stability for us is measured at a dynamics level. So we don't need external sensors to stabilize a robot. We don't need a gyroscope or an IMU or anything like that. We guarantee stability a priori through mathematics. So this is really a mathematical approach to robotic walking. And the idea here is to not have to fine-tune parameters on the robot and spend all this time trying to get this perfect combination of things, but rather to simulate something, to prove something is correct, and put it on the robot and have the robot work exactly as you predicted in simulation, is closing that loop and making it a perfect circle.
That's great. So what's the next step in this research?
Well, the next step is to get robots that achieve the kind of walking that we've always wanted from science fiction. That's been my goal. I've been a big science fiction buff my whole life. Asimov has influenced me a lot. And the idea is that robots should not have to only walk on flat ground. They should not have to walk on a boom in 2 dimensions, but actually getting stair climbing, jumping, flipping, running, and all those motion primitives that humans do so well on a full robot in a very natural and human-like way. And the applications of this are really, as far as you can imagine. I mean, anywhere from space exploration to disaster response, going into nuclear reactor plants that are melting down and having the robot walk in there with low light and low sensing, all the way to prosthetics and exoskeletons and, down the line. I think it's somewhat of a travesty that we need wheelchairs in this day and age. I feel like we should have the technology and engineering to make people walk even if they don't have the ability to use their own legs. And that's really the end goal of all this work.
Great.